All right. So a slope field is a representation of infinite solutions to a differential equation. I know that these can be annoying to draw sometimes, and I get that, and I get annoyed by them too sometimes. However, the concept of what they are does kind of geek me out. We're going to draw a picture that represents an infinite number of graphs. That's cool. That's so cool. You can disagree, but I'm right. That's so cool. You're going to draw something that represents an infinite number of graphs. It's kind of like, you think of like y equals x squared. All you get is that one parabola. We're going to draw an infinite number of parabolas all at the same time. Neat, guys. Neat. You're all on board, right? Yes. Cool. Yeah. All right. Now, if I know, I just love it. It's cool. Like you can draw an infinite number of graphs all at the same time. All right. Now, if your differential equation only has x in it, if there's not a y, it means all of your columns are going to be the same, which is nice. You can knock out whole columns at once. If you only have y, if there's not an x at all in your differential equation, then all of your rows are going to be the same, and you can knock out a whole row at the same time. And those are also always super convenient. It's not a slog like you have to go through point by point to draw the thing. So we're going to do a lot of stuff with each of these. I only have 5 problems on here, but we're going to do a lot of things because I want you to make some connections between what we did last time and what a slope field is. So we're going to draw the slope field, describe what they look like. They're parabolas, they're exponential, they're increasing, I don't know, whatever. We're going to solve for the general solution, which means C will stay in there. We're going to do a specific solution or a particular solution. I'm going to give you an initial condition. And then we'll draw that specific solution in on the slope field. So we're going to do a lot of things to kind of connect it all together. So looking at this first one, what do you notice about your differential equation? No y. There's no y. Do you guys all see that? It's only x. We're going to knock out whole columns at once. Fine print for this. If you are very type A and things must be perfect all the time, you're going to need to take a few deep breaths because this isn't going to be perfect. It's going to be good enough. All right. And you're going to kind of not be able to see the whole thing until we get it all drawn. You kind of have to trust the process until you get the whole picture. Okay. So let's start at the first column here. For every single one of these points, and it looks like, that game you play where you draw a line and a partner draws a line and then you try to put like your initials. I always think it looks like that, which it does, that little box game. Anyway, for this entire column, x is what? -2. Okay, -2. So if you plug -2 in for x, what are you going to get? 1 minus -2. 3. That means for each of these, the slope, dy dx's slope, should be 3. Up 3 over 1. I don't know. About like that. Good enough. It should be positive. It should be fairly steep. Good enough. Right? Just in relation to each other, they need to make sense. So when we do the next column, what is x for every single one of those points? -1. So if you plug in -1, you get 2. So if this is 3, 2 just needs to be like a little less steep. Do you get what I'm saying? So just in comparison to each other, they need to make sense. So I don't know, maybe about like that. Again, it's good enough. Just a little less steep than the one you just drew. For the next column, what is x for every single one of those points? 0. So if you plug in 0 for x, you get 1. So a little less steep than what 2 would be. So what is x for the next column? 1. 1 minus 1 is 0. Now those ones will be perfect because a 0 slope is horizontal. So those you will be able to get perfect. You're going to be okay. All right, what is x for the entire last column that we have there? 2. So if you plug in 2, 1 minus 2 is -1. Now listen, if this is +1, -1 needs to look like that much, but just Negative. Yeah, the other way. Okay, so again, just in comparison to each other, they need to make sense. Cool, we just drew a slope field. Remember that from last year? Medium? Okay. It's not random, they're slopes. Okay, so description. Do you see how if you followed along with the slopes, what kind of a shape of a graph would you get? A parabola, a U shape that is negative or upside down. I'm going to say reflected parabolas. How many of them? Infinite. We just drew infinite parabolas. That's so cool because there would be one here and one here and one here and one here and one here. And the slope field would keep going off the paper and down the hallway, you know? So like you just drew an infinite number of graphs, which is neat. I'll let it go now, but it is cool. All right, so we're going to solve the differential equation for the general solution. All you need to do is move over the dx. I also recommend putting a 1 in front of the dy. If you were still shaky on what we did last time, cool. We're going to do a whole bunch more of them right now. All right, your next step is to integrate. So what do you get on the left side conveniently? Yeah, y equals, which is good because you want y alone. And then this antiderivative. For 1, you would just get x minus 1/2 x squared plus c. That's your general solution. And now you want to make sure that that makes sense with what we said it should look like. Would these be reflected or inverted parabolas? Yes, it's squared, and that term is negative, upside down, concave down. Okay. Now we're going to write out the particular solution for the initial condition 0, 1. So over here, if you plug in 0 for x and 1 for y, what is our c value going to be? 1. I was hoping we could just do that in our heads. It's going to be 1. So your particular solution would be y equals x minus 1/2 x squared plus 1. When you go to draw in a particular solution, and they sometimes do this on the free response, I don't know if you'll get one or not. They'll put a slope field on there and give you an initial condition, and you have to start at that point and then draw in. You just swim with the current. I kind of don't have a better explanation than that. You just sort of go where the slopes are telling you to go. You shouldn't run into any of them. You should flow along nicely with them. And you have to draw all the way to the edge of the graph. That's the only thing that'll sort of lose you points on there is if you don't go all the way to the edge of the graph, they'll take off for that. So we're going to start at the point 0, 1, which is right here. And do you see how this is a slope of 1? It's kind of telling me to go this way. So you're just going to sort of like head in that direction. And you don't really want to bump into any of the other ones, but do you see how I'm sort of just flowing along with them? And it like... they're sort of directions. They're telling me where to go. It's saying, go this direction. And you just need to make it go all the way to the edge. For example, if I stopped here, they won't give me credit for it. You have to go all the way to the edge of the graph. So that is one of the infinite number of parabolas that we've got there. Just go further than you think you need to. No, I wouldn't go off the paper. But go at least to the edge of the graph. Okay, well, you're being a little extra. Go ahead. Because that's me. I put in the directions, solve it for the general solution and solve it for a specific solution. I'm just having us practice both. That was a me. I put that in the directions kind of thing. All right, let's try another one. What do you notice about this differential equation? There's only y. We're going to knock out whole rows at the same time, right? So let's start with this first row. What is y for every single one of these points? 2. If you plug in 2, 2 over 2 is 1. So the slope for each of those should be 1. Good enough. All right, what is y for the entire next row? 1. If you plug in 1, you get 1/2. So if this is 1, 1/2 should be like less steep than that. So just compared to each other, they need to make sense. What is the next row going to be? Now, if you get a whole row that's 0, and we're going to describe this in just a minute, what does that mean the graph has? a horizontal asymptote, okay? What is y for the entire next row? -1. If you plug that in, you get -1/2. So it should look like the positive 1/2, but going the other way. You should make them the same amount of steepness, but just reflected. And then the last row is going to be -1. So when there's a horizontal asymptote like that, what graph is that? It's not quadratic or cubic or exponential. Good. So exponential horizontal asymptote, and I'm going to just abbreviate, horizontal asymptote at y = 0. So it's a swoopy graph. Actually, it's an infinite number of swoopy graphs. All right, we're going to separate our variables. To get this y moved to the other side, you would have to divide. So when I write it over here, it's going to be, or yeah, you could write dy over y. My preference is to write 1 over y dy, but that just comes down to like how you like to write it. No one's right and no one's wrong. That's how I prefer to write it. All right, equals, now careful, there's still a 2 on the other side, but where is it? The bottom. So it's not 2, it's actually 1/2. So 1/2 dx. Antiderivative. So what's your antiderivative of 1 over y? Yeah, ln, good, equals, antiderivative for 1/2 would be 1/2 x, good, and then plus c. And we're going to make this be the general solution. So we're going to leave the c in there. We're going to go ahead and solve it. How do you cancel out ln? E. Okay, I'm going to just talk you through this because we went over it last time. E is a number. C is also a number. And leave a little gap here. So you bring c out front. It's just one big constant. And then it's e to the power 1/2 x. I left a little gap because when you get rid of the absolute value, it's plus or minus. If you think about your slope field, your exponential swoopy graph could be up here or it could be down here. It depends on what your initial condition is. Now the first one was real simple, so I just kind of talked you through it. For this one, you can't just start plugging into this result that you ended up with. It doesn't work like that. You have to go back to this step. Do you remember me drawing an arrow next to it? Okay. You have to plug in your initial condition here. All right. So we're going to plug in 2 for x and -1 for y. So it's going to look like this. ln absolute value, which is why we have that there, because you can't ln a negative number, equals 1/2 times 2 plus c. And we're going to figure out what c is. So absolute value of -1 would just be 1. What is ln of 1? Yeah. 0 equals 1 plus c. So c is -1. You cannot just make this negative. It doesn't work that way. You have to go back and do it again. And you're like, we don't like that, Ms. Claude. I'm just telling you the way it is. Okay. So you're going to recopy this line that has the arrow on it. Exactly like it looks, but put -1 instead of c. And then you can solve it. You have to go back and do it again. I'm sorry to be the bearer of bad news. But we only have one step here to get rid of ln. You do e, again, leave a little gap. Now, do we put the plus or do we put the minus? The general solution, you keep both of them because it's an infinite number. Now we're going to choose, do we want plus or do we want minus for this one particular answer? Good. Our initial condition has a negative output, so we want the negative result. And now we're going to tie this together. And see, I just want you to make so many connections here. When we draw it in on the graph, you'll see that it's negative, that it's reflected. We're going to start at this initial condition, 2, -1. So 2, -1 is right here. So you start at that point, and then you just kind of go with the flow. It's going to do something like this. This is your exponential graph. So do you see how it's reflected, how it's upside down? It's negative. So you can kind of make all those connections. I'm gonna have you guys try one, and then we'll do like a little brain break. Okay, because I know there's like a lot of parts to these, so these problems take a long time. I'm gonna have you guys try number 5 on the back. Talk to each other. I got this. What did you get? I think this is the next step. What do you think? I want you to try number 5. And when it seems like everyone's drawn the slope field, like I'll walk around, I'll draw it up so you guys can check it. And I want you to try the rest of it and see if we can all get the same thing here. Okay, so we got something that looks like that. Your description is that they are cubic graphs, little wiggly things. And when we do our antiderivative, like when we solve this differential equation, you're going to be able to make the connection and see that it's cubic. To separate, you're just going to multiply over your dx. Antiderivative of just 1 dy, just be y conveniently. And then what do you get on this side? Yeah, x cubed plus c. Perfect. Easy peasy. So let's do our specific or our particular solution for the initial condition 0, 1. This one is simple enough we can kind of just look at it. If x is 0 and y is 1, c is just going to be 1. So it's your cubic graph moved up 1. So you're going to start at that point 0, 1, which is right here. And then you just flow with the current. I don't really have a better explanation than that, but it has to be really wrong for them to not give it to you. You're going to start out kind of with a 0 slope, and you don't really want to run into any of the other ones. You kind of want to flow like in between them, sort of. It should be something like that. And go all the way to the edges. How'd that go? Okay. I'm going to just do one of the other ones. I typically put more on here than we need. I'm not trying to torture you with these graphs. Plus, you're going to do a classwork anyway. We're going to go back and do number 3. Why would number 3 and number 4 there too? Why are they harder questions? They have x and y. I guess I shouldn't say harder, but just more annoying because you can't knock out whole rows or whole columns at the same time. The first thing you want to look for is a place where you get 0 over 0. What is that called? It begins with an I. Indeterminate, okay? When x is what and y is what, will we get 0 over 0? When x is 0 and y is negative 1. At 0, negative 1, there should be nothing. It should be blank. So here's what I tell my students to do. Just sort of bold that point. That is a me thing. That is a Miss Cole thing. It's not going to say to do that anywhere else. But the reason I say to do that is if I look at my work and something's blank, I'm going to think I forgot or I messed up. So I just bold that point to remind myself there should be nothing there. Does this make sense? Okay. Now, we can knock out like one column and one row. When y is negative 1, your slope should be what? 0. So everywhere that y is negative 1, you can put a 0 slope. And then everywhere that x is 0, you're going to get a 0 denominator, which means undefined, and so it'd be vertical. So you can put vertical slopes everywhere that x is 0. So we knocked out a little bit of it. We are going to kind of have to slog through point by point for these ones on the left side, but good news, what do you think is going to happen with them? It's going to get reflected. So we kind of just need to do like half of it, or do you want to do the positive half and we'll reflect it over there? Okay, we'll do that. So this point right here is the point 1, 2. You're going to have to follow along with me here. I know it's not super fun, but we'll make it through. All right, 1, 2. If you plug in 1 for x and 2 for y, what do you get? 3 over 1, which is 3. Like that. Good enough. All right, this point is 2, 2. If you plug in 2 for x and 2 for y, you're going to get 3 over 2, which is 1.5. So if this was 3, 1.5 should be like less steep. Do you get what I'm saying? Like a little bit less. Good enough. You have to take a few deep breaths. It's going to be okay. Trust the process. It's not going to look like much until you finish the whole thing. All right, what's this point? 1, 1. If you plug in 1 for both x and y, 2. Now, if this one's 3 and that one's 1.5, 2 should be kind of in between them. Again, it's good enough. Just let it go. Yep. This is the point 2, 1. If you plug in 2 for x and 1 for y, you get 2 over 2, which is 1. That's the least steep one that we've done so far. So less steep than kind of everything else that we've done so far. All right, we're getting close. You're hanging in there. All right. This is the point 1, 0. What is that going to give you? If you plug in 1 for x, 0 for y. Yeah, 1, right? Now, we just did 1, so it should look the same as the one that we just did. All right, 2, 0. That would give you 1/2, so that should be even less steep. Starting to look like something. All right, this is the point 1, -2. So if you plug in 1 for x and -2 for y, you're going to get -1. And then last one, 2, -2. That's going to give you -1/2. So less steep. Now what you want to do is take all of those and reflect them to the other side. I know, doesn't it look cool? There we go. It doesn't really start to look like much until you get to the very end. I always think that one looks like a lion's mane for some reason. Like if the point at the center was his nose or something. I know you can't see his eyes, but I don't know. It reminds me of a lion's mane. Or maybe like a firework. Now, when we go to describe them, you're like, what in the world is this? You need to think of a graph that is indeterminate at a point, meaning you cannot get a derivative. Can you think of a graph? And I'm trying to mime it for you. It is absolute value where the point is going to be at 0, -1. Good. So it's absolute value with the point at 0, -1. If you were like, that didn't seem very obvious, that's why I'm your teacher and I'm leading you through it. Okay. But you need to think of a graph where you can't get a derivative. Remember, not differentiable due to sharp edge kind of thing. Okay. That's it. All right. Here we go. We need to move over this y plus 1. We're going to do that by dividing. So when I move that to the other side, it's going to be 1 over y plus 1 dy. And then what is still left on the other side? 1 over x. And then dx. All right, antiderivative. Your antiderivative of 1 over y would be ln of y. So this is just going to be ln of y plus 1. And then the other side is going to be ln x. You're like, oh my gosh, this is alphabet soup. There's like not even any numbers in it. Plus c, thank you. I wrote it, but I didn't say it. All right, now you want to get rid of the ln. So we're going to do e. E is a number, c is a number. So it's going to be c e to the power ln x, absolute value of x. It's actually really important. When I get rid of this absolute value to solve for y, what am I going to put in front? Yeah, plus or minus. And what happens to this e and this ln? They cancel. And then you've got one more step, and you're like, oh my goodness. So it'll be y equals plus and minus, because it's an infinite number of answers, c, absolute value of x. What goes at the end? -1. Good job. Why is the -1 super important? It's where the point is, the point of your V shape. Now, for the sake of time, I'm not going to make you work all that out again. I'll show you a little trick that we can do for absolute value. It's telling us to start at -2, 0. So walk with me on this so we don't have to write it all out again. All right. You're going to start at -2, 0, which is right here. I know I said you don't want to run into too many of the slopes, but each side of an absolute value is linear. Do you get what I'm saying? They're lines. Okay, so we are going to kind of run into a few other ones. Well, I guess we'll run into one other one. But you want the point of the V to be there. And then the other side is going to go this way because we have symmetry. So let's see if I'm going to take you back to algebra 2. This is where you learn this, all your transformations. Is it positive or negative? Do we want the plus or the minus? Positive, it's facing upwards. Negative would be if your point was here and it faced downwards. All right, so we want positive. What is C? C is the slope of each one of these lines. 1/2. Good job. Bless you. So 1/2 absolute value of x minus 1. The minus 1 is what brings it down 1 and puts the point there.